I could guarantee a problem like this on the quiz. And so I give you a function, and then I'm going to tell you to find the equation of the tangent line at a certain place on that function. Okay?
How would you find the intercept? Because you can only plug.
We're gonna go through that.
Okay.
Now, here's the thing about this, though. It does not matter what this is. This right here, and no matter what number this is, no matter what, you could always find this. It does not matter what f is itself. I mean, unless f is not differentiable. But, okay, so let's think about this, and anytime I get something like this, right, when I see, find the equation of something, and it's something to do with graphing, what I'm immediately going to do first, just off to the side of my page, is say, okay, what does f look like? I have no idea. But maybe it looks something like this. I don't know. Who cares? That's not really the point. The point is, okay, we have this. We need to find the equation of a tangent line to this thing at some value. Again, doesn't matter what picture I drew. I'm just going to say, okay, we're here at the square root of pi over 3, wherever that is. And we want to know what is the tangent line right here. And so, okay, there we go. In other words, find the equation of a line. Now I'm going back into Algebra 2, Algebra 2 mode here, and I'm going to say the equation of that line is what?
Y equals mx plus 1.
Right, there you go. And so now there's just two things we need to find. We need to find an m, and we need to find a b. Which one of these is going to be easy to find? M, right? Because why is that the case? How do we find the slope right there?
The derivative.
The derivative of this at the point we care about, right? And so I'm going to take the derivative, and then I'm going to plug in the point we care about, and it will tell me what that slope is right there. So take the derivative of this, and what do we get?
Negative sine of x squared.
Negative, right? Okay. So let me say this. We took the derivative of the outside stuff, which was cosine, and that derivative is negative sine, and we leave the inside stuff alone. Then we multiply by 2x, the derivative of the inside stuff. And so we have that our derivative is equal to negative 2x sine x squared. And I'm almost always going to clean it up that way, where I put all the constants out in front of sine. Sine and cosine will be like the last things that I write. That's just how it is. Okay, so then what is m? How do I find m? What do I need to do? Plug in into here. And that will tell me, this is the function which tells me the slope at any given point. Here's a given point right there. So I'm just going to plug it in. And this function will tell me what it is. So we have root pi over 3 sine root pi over 3 squared is just pi over 3.
So that's root 3 over 2.
And so, yes, sine, just to be sure, we have our 1 to root 3. This is pi over 3 right here. And so opposite over hypotenuse, right? Because sine is opposite over hypotenuse. That means that this guy is, just like you said, root 3 over 2. So we have minus 2. I'm going to rewrite this like this, because maybe, who knows? Who knows? Maybe something will work out. Maybe it won't. Maybe it will. Who knows? But sine of that, we said, was root 3 over 2.
Everything cancels.
Oh, that's nice that everything cancels. Yeah. That's nice. It might not have, right? That could have been a root 5, and that's a root 7, and that's a 2 and a 5, right? Or like a 7 and an 11. And you have some big ugly thing, but that right there is your slope, right? No matter what that is. Whether or not you could clean it up or not, that's your slope. Yeah. Just to really drive a point home, I'm not even going to simplify this yet. It would be too easy to simplify. It would come out to be negative root pi. Really easy, and I could plug it in really easy. I'm not going to do that. Just to make a point that right now, what we have is negative 2 root pi root 3 all over 2 root 3, like that, x plus b. Okay? Yes, my life would be easier if I'd simplified it, but it doesn't matter. Right, I'm just trying to show you, just like you said at the beginning, right? Like, well, how do we do something, even if? And what I said was, it does not matter what this is. It doesn't matter what this is. In the end, you're going to have something where you've plugged that in, and there's some expression, and that's what you have. Now, do we have enough information to find b? we need a point. All right, have you been given a point?
No.
Not really. You have been given a point. You just don't know where that. How do we find the other part of that point? How do we find what value that is?
Well, we can just plug it in.
Just plug it into which?
The first one.
The first, yes, because this is the function f of x that I drew. I'm pretending it looks like that. It might look like that, I don't know. But when I plug something in, it touches that function, right? And that's the whole point. A tangent line has to touch the function at the given point, so that's what I'm doing, right? And so when I plug in a what into this, I get out a what?
Cos of pi over 3.
When
you plug in.
when I plug in a what?
Root pi over 3.
Root pi over 3, I get out a, let's see,
1/2.
cosine root pi over 3 squared. So that's cosine pi over 3, which is what?
1/2.
1/2, right?
Or
Back to
negative.
the triangle, 1, 2,
No, not negative.
not negative. Nope, we're in the first quadrant, and so adjacent over hypotenuse would be 1 over 2, so yeah. Root pi over 3, this is just 1 over 2. So we know that when we plug this in, out pops a 1/2 right there. Now can we find this? What do we need to do?
Plug in for y next.
Plug in what for what?
1/2 equals.
For what?
Y.
Oh, 1/2. So the output of this line, yeah, the output of this line had better be 1/2 when the input to the line is that guy right there. Root pi root 3 over 2 root 3. Now we plug in a what? Root
Pi over 3.
pi over 3 plus b. Can we get b by itself?
Yeah.
Yeah, and do we need to simplify anything?
No.
No, we don't, do we? And this was the point I'm trying
Well,
to
we
make.
need to subtract that.
We need to subtract it over. And since it's a minus, I'm going to go ahead and do it like this. It's a minus, right?
Yeah.
Right, there's that minus. So I'm just going to add it. And we'll have 1/2 plus 2 root pi root 3 root pi over 2 root 3 equals b. Okay? And I'm doing this deliberately. I want this to look really ugly because it does not matter how crazy your function is. You'll have some value. And maybe perhaps that value is just f of root pi over 3. Like if you're working with a really crazy function, evaluating it might be too much, but you could say, well, that's what it is. Whatever that value is going to go right here, right? Like that's what it is. Or like it's going to show up right here. You see what I'm saying?
Yeah.
And so my final answer, if I were just being lazy and not computing anything, I would say, okay, it's y equals -2 root pi root 3 over 2 root 3x plus this big ugly thing, 1/2 plus 2 root pi root 3 root pi all over 2 root 3. And then, I mean, if we wanted to. So this is your answer, and you're perfectly good to go. Although that's probably even more work than just simplifying it at first.
Yeah.
Right? Right? And so, like, how would you actually have done this when you found that this was -2 root 3 root pi over 2 root 3? You would have canceled them.
Yes.
And you would have said, the slope m is minus root pi. So what then would you have done? Well, you would have come over here. And you'd say, okay, now y equals minus root pi x plus b. And I know when I plug in my root I get out that 1/2 equals -root pi times root pi over root 3. That's what that is. Plus b. This is kind of nice because that's 1/2. The root pi's become just pi. And the over root 3 stays over root 3, so plus b. So therefore b equals 1/2 plus pi over root 3. And I would have put that into here to give me a y equals minus root pi x plus 1/2 plus pi over root 3, which indeed is what this would reduce to, if you cared to do all of this. There's a root 3, there's a root 3, there's a 2, there's a 2. 1 pi over root 3, that's all the same. You could double check that. That's the exact same thing as this.
Yeah.
But that's the idea, right? You could just go, mechanic, right? Like just do the mechanics of this. And like you don't really need to use your brain. Like it's just you find the derivative, plug in the point, whatever that pops out, you just plug it into your equation, right? And so on and so forth. It might look really, really ugly, but it still works, okay? Questions on that? No, I wanted to do one that was going to get really ugly, and that got really ugly. So, mission accomplished. All right, questions about stuff? Anything pop up while we were thinking? Okay. Yeah. We're gonna move to black. Here we go. So here's another type of question I'm probably gonna give you. I'll do something like this. And I'm gonna ask you to draw the derivative. Here's f. It might not look as crazy as this. It might. We'll see. And I'm going to ask you to draw the derivative of this guy.
Okay. Just based on guesstimation.
Just estimation, right? But there are at least 2, 3... There are 3 places where we could immediately get values.
The vertexes.
Yeah, you could think about those as vertices,
Yeah,
but the maxes and the mins, right? Wherever you see a max or a min, or if you're thinking about this as a parabola, like that looks like a parabola right there, then yeah, that point would be its vertex. But we could say right here, we know that the slope is what?
0.
The slope is 0, and therefore its derivative must be 0. So if that's f, and we're drawing f prime, I suggest that the first thing you do is find where the slope is 0 and mark that here. Now something crazy is going on here. We'll have to figure that out. Is there another 0 part derivative?
Yeah, maybe right there.
Is this what you're talking about?
Yeah.
Okay, yeah, then that's it. That's also a 0 right here.
And then there's a corner.
There's a corner, so what happens?
There.
Yeah, it won't be differentiable there, but we should take that into account here. We should be able to get some info on it. So first, let's go do, now I'm pretty sure, I don't know for certain, but something's telling me that if it blows up there, it's gonna blow up here.
Yeah.
Probably, right? And we'll see. We'll see what happens. But now, okay, so on this side, is the derivative positive or negative when we're over here?
Oh, it's positive.
Right, the derivatives, and it looks like it's positive and it's getting smaller.
Yeah.
So it's a big number that gets smaller and comes to 0. So maybe something like this.
Yeah.
Okay, it looks like it's coming from very steep and going straight down. It does that. Now that we're over here, is the derivative positive or negative or?
It's negative. And
It's
getting smaller.
negative,
Yeah.
so that it comes down. It looks at some point it starts climbing back up, so it's going to get negative and then come back up.
Yeah.
Right? And then maybe I did that right, I did that wrong. We're going to talk about this soon. This is called an inflection point, and it will correspond to the minimum here. But you could tell this is like the derivative 0. Now the derivative is negative, and it's getting more negative, more negative, more negative. Oh, stops getting so negative. It gets less negative, back to 0. That's what's happening here. It's negative, it gets more negative, more negative, more negative, until it stops getting negative. It's still negative, but it's coming back to 0, and that's what's happening there at that point. Now, as we go from a 0 slope over, what happens to the slope?
It gets more positive. It approaches infinity.
It looks like it's approaching infinity, so I think it's pretty safe to do something like this. Okay, now, On this side of it, is the slope positive or negative or what?
It's
Positive and
It's positive.
Positive,
But
right?
it's
So
like infinity
it's
there.
still, yeah, and it looks like as we go this way, the slope is getting closer to infinity. And so I'm going to say, okay, from here back, the slope is positive, so it should be positive numbers, and it's getting bigger as I go back towards here. So it should look something like this, right?
Yeah.
Okay. Now this thing. This looks like pretty much a constant, the way I drew it. It looks like a constant negative slope. So maybe I don't want to
There's a
draw it
jump.
like that. Let's do it like this.
But then there's no. I guess there is.
Oh, there is now. There's a corner. Okay. So it's nice and smooth. I'm not trying to mess with you. Although, if you really wanted, like, I mean, at some point from there to there, that's just a negative. It's constant. It would be like a constant negative number.
Yeah.
But I'm not going to nitpick about that kind of stuff. If it's curvy, the derivative's probably also curvy. And so it's easier to draw that way. Okay. So here we go. It's positive, and then it hits 0 right here. Then what happens to the slope?
Negative.
It's negative, and it looks like it's getting negativer, right? And so, okay, it comes down like this, maybe. It's also kind of a curvy thing, maybe.
Yeah.
Until all of a sudden it stops, and now it's no longer a negative slope. It's actually quite positive. And I did not mean to draw this like it's straight up. Let's say I didn't draw it like it's straight up. Let's say that I drew it where you could tell it's not straight up, but it does something like this. Okay, so it jumps from having a negative slope to magically it has a positive slope.
Yeah.
So magically it has a positive slope. And it looks like it's positive and gets less positive. So maybe it's positive and gets less positive, so maybe it does something like this. I don't know. We don't really know past here.
Yeah.
But I would also, just to be certain that we're all on the same page, I would put a hole right here. And on the quiz, I'll have like a 1, a negative 1, so you could be certain that you do all your stuff like this. This might be like a 2. And so when you draw your own, you could do this kind of stuff. And I would have like a 4 here, so you could say yes here at 4. It's not defined, right?
Yeah. Okay.
Right. Something like that. There's tons of practice in the book for these types of things, and I would suggest that you look at them, because I think I'm almost certainly going to give you one like this. Almost certainly. So good odds
Okay.
that spending your time doing these examples in the book from chapters 3. You can take a look at the end of chapter review. Of course, we have not finished the chapter, so not all the questions in that will be pertinent, but they might help you. Everybody get this? Everybody getting this? All right. Here's something. I want to do this now. I think I do want to do this now. Might as well do it now. Okay, we'll just do this now. Let's do this together. Let's do this as a family. So, let's let f of x equal cosine x. Now, what would f prime of x be? Negative sine x. What would the second derivative be?
Negative cos.
Negative cosine, right? Because negatives are constants, they come along for the ride. The derivative of sine is cosine, and so the negative came along for the ride. There we go. Now what's the third derivative?
Sine of x.
Yeah.
Positive sine. And so we're almost back to where we started. It would take a fourth derivative, and what do we end up
Now
with?
we're back.
Now we're back to where we started. Okay? So if I said, okay, what is the 22nd derivative of f? So now I want f, the
Maybe
22nd.
negative cosine.
Let's check, right? So when it's 1, it's this. When it's 2, 3, 4. So this will be f5, f6, f7th derivative, right? The 8th derivative. Everybody got me on that?
Yeah.
What I'm saying here? It just keeps rolling around. And so now we just need to figure out, okay, if that kept on up to 22, I guess when it's divisible by
By 4.
4, right?
That's 2 more than 20.
'Cause 20
Whenever it's
is
divisible by 4, you're back to cosine, right?
Yeah.
And so 20, so we could reason that the 20th derivative must be back at cosine. And so then the 21st derivative would just be what?
Negative sign.
Negative sign, meaning that the 22nd derivative, which we care about, is what?
Negative cosine.
Negative cosine. Okay, so that's cool. So you would know that that's negative cosine x. And if I asked you, what is this? Evaluate this.
Of 0.
And 1, negative 1.
Negative 1, right? Because that's that.
Oh yeah.
Plug in a 0. That's the 22nd derivative. Plug in a 0, you would have negative cosine of 0, which would be negative 1. So I might just give you, here's f of x equals this. Find this, and I might have you evaluate it at a place.
Okay.
I might give you something like this and tell you to evaluate I might just tell you f of x is equal to cosine x. Evaluate each one of these.
Okay.
And you should know what to do. You're going to have to first take those derivatives. And then once you've taken the derivatives, then you plug in your value, right? Because you can't just do this. You can't say, well, hold up, f prime, oh, at pi, I could just plug in a pi. Because you get, oh yeah, cosine pi, that's negative 1, okay. Well, that doesn't help you in that, does it? Right? Because we're not saying take the derivative after you've plugged this in.
Yeah.
We're not saying now take the derivative, because that would just be 0.
Yeah.
Right? So remember, like this, in order to get to this place, you first have to find out what these formulas are before you start plugging in pi's. You can't plug in your value before you do it. And that's true with any function, right? Imagine I have any function here. Here's any function, and it looks like this. And then I happen to know that here at pi, we get out a 2, okay? That doesn't help you at all with the second derivative, or the next derivative. Those values might have nothing to do with anything, right? So you would first need to go through, find all of the derivatives, get a formula for the derivative, which is kind of like what we did, right? We took the nth derivative, happened to be 22nd, and we were able to find out that it was minus cosine x. Then from there,
Is there a
we
formula?
there is a formula. We're going to be coming back to this. let me tell you, boy, we're coming back for this bad boy. And yeah, and so there is a formula for the nth derivative of that, and yeah. I'm not going to ask you to do that. I will ask for something like this, or like what we did before, find the 22nd derivative and then maybe evaluate it at a point. But in order to evaluate it, you need to find the value of the function first. You need to find the actual function itself before you can plug something in. Okay, all right, cool. Couple bookkeeping things, because I might very well ask you a question involving velocity. Like what I'm going to do is say your position as a function of time is given by t cubed minus 2t squared plus 3t minus 4. And then I might ask you, so I'll tell you, this is the position of a particle in meters and at time t seconds. And we want to know, so this is the position in meters at time t in seconds. And I'm going to ask you, what's its velocity at 1 second?
Is velocity the second derivative?
Nope.
It's the first derivative.
Yes, and this is what you need to remember, because this is going to be ubiquitous for the rest of your life. Now that you've taken calculus, you will be expected to know that the derivative of position,
And then it's acceleration.
the derivative of position is called velocity. And it's a signed amount. It could be negative. It's not the speed, right? Speed is only, it doesn't care which direction you're going. It's just the absolute value of where you're going. Velocity, on the other hand, can be negative. So like if S looks like this, well, from about here to here, you have a negative velocity because your slope is negative. So what does that mean? It means that you, instead of going north on the highway, this was the time where you were coming south on the highway, right? A lot of different ways of putting that. Is everybody with me on that?
Yeah.
Okay. And what's acceleration? Or rather, I should have said, what's the second derivative?
So
Yes. And so velocity we usually denote with a v of t. The second derivative we usually denote a of t, and that's acceleration. This is standard. And s is almost always used as position. Why? I don't know. But that's why. It just is. And so, just so you know, okay, like you will be expected to know all of this. And you'll have to do one of these. So how do you do this? How do you find the velocity at 1 second?
I'll find the derivative.
Okay, what is it?
3t.
Okay, so s prime of t is equal to
3t squared
3t squared
minus 4t
minus 4t
plus 3.
plus 3. And so what is the velocity at 1 second?
Plug in a
Make it
1.
What do we do?
Plug in a 1.
Plug in a 1. S prime of 1 is 3 minus 4 plus 3. It's
Something. 2.
2. Positive 2 sandwiches
Meters per second.
meters per second. I will be judging you on that, right? Because I've given you position in meters. I said, this is what this prompt says. I've given you some function. It looks like this. Input is t in time, seconds. Output is in meters. And its derivative at any point is the slope of this line right here. And let's say this was 1. That slope has units. It has units of rise in meters, right? Meters minus meters is rise. Run is seconds minus seconds, so it's seconds. And so this quantity that we have is meters per second. That's why velocity is the way it is. That's why the next one's acceleration, and so on and so forth. But you will be expected to know all of this. And so if I ask you about velocity, I might ask you, when is its acceleration 0? How would you do that? If I said when, so here's this work that you've done, and now the follow-up question is when, meaning at what time, when is the velocity, or no, when is the acceleration equal to 0?
So you
And
take
the
the
second
derivative
derivative.
and then find
Let's take the second. So how do I take the second derivative?
Take the derivative.
It's 6t minus 4.
Right, so the 2 jumps down and hits the 3, giving me a 6. 2t to the first. Now what?
Minus 4.
What about the 3?
It's gone.
It's gone, okay? Now, when is the acceleration equal to 0?
At the x-intercept, right? So you plug in a 0.
For t?
Yeah. Right?
S
Oh, no.
double
for, sorry,
prime, that would tell you the acceleration
You
at
said
time
equals
equals 0.
Yeah.
So this would be, this is the acceleration when time is equal to 0. But here we're saying when is the acceleration equal to 0? That's when the output is equal to 0. And that, here's another thing, right? This is why I said it the way I did. When, I'm asking you for a time, right? I'm giving you an acceleration, I'm giving you an output, right? Since this is a of t, and I'm saying, at what time? If you plugged in a time, you wouldn't be able to answer at what time.
Yeah.
Right? That's another way that you could check yourself with like word problems. It's like, wait a second, what are they asking for? What time? Well, then t ought to be something that I'm looking at. So you say, when is the acceleration equal to that? And you get 6t equals 4, so that t equals what? 2/3. So its acceleration is 0 at 2/3. Okay? Or any kind of thing like this, right? When is its velocity equal to 0?
How do you measure acceleration? It's not meters per second. It's like
So, let's think about this. this is a graph of a function. And it has, the input is time in seconds, and its output is what? What's the output of this? What's the unit?
Meters. Oh, yeah, it's out.
It's meters
Yeah,
per
yeah.
second. Now the output of this function, s prime, or the velocity, the output of it is it's not a speed, it's a velocity, but it's how fast you're going, right?
Yeah.
And so when you do this again and you find the rise over the run, the rise is now in terms of meters per second. The run is now in terms of seconds, and so you have meters per second.
In this case, then it's
Or
meters
meters
per
per second squared. And that's what acceleration, that's the units of acceleration. Meters per second squared. Or meters per second. So your speed, which is meters per second, how is that changing?
Yeah.
How is your speed changing as time changes? That's what acceleration is.
Yeah.
Okay? Anything on this before we move into other stuff?
What's the third derivative?
The third derivative is called jerk.
Oh,
And it is sometimes used, so S1, 2,
So
3,
how
the
your-
third derivative, sometimes
How
J.
fast your acceleration changes?
How fast is your acceleration changing? And if your acceleration changes fast and you're in a car, you'd say, wow, it's jerky.
yeah.
Yeah.
That makes sense.
That's why it's called jerk. Yeah. So, and then there are more, but like, I mean, there are infinitely many, I mean, technically, there's like infinitely more derivatives, but like, how useful are they?
Change
Can you measure
change
that?
of acceleration.
Right, exactly. That's just a pain. So, let's do one more of those. So here's the trajectory. I want to make this easy. Let's think. So, oh, this is not going to be easy, but whatever. We'll just do it this way. Yeah. We'll see what that does. Here's a trajectory of a particle. Okay, this is a trajectory of a particle where s is in units of meters and t is in units of seconds. Okay, same setup as before. And now I want to know when does the particle stop moving?
So when is its velocity 0?
There you go, right? So that's the first part of this done. We were given a function, and when does it stop moving means when is its velocity 0, right? That's what that means. When, at what time, questioning what input gives me an output of 0. Velocity is the first derivative of s of t. So what do I need to do?
Take
Take
the
the
derivative.
Take the derivative, and what does that give me?
3t squared.
3t
Minus
squared
6t
minus
plus
6t plus
3.
3. And we want to know when is that equal to 0. What do I do?
Set it equal to
Yeah.
Set it equal to
Quadratic
0.
form.
Oh, there might be multiple.
Quadratic form.
Factor out a 3.
Factor out a
Yeah.
3. I like that. That's what I was like, oh, what do I do? What do I do? What do I do? And I couldn't see what I was doing in my head as I did it. This one works out to be nice.
Yeah, okay.
Everybody got that?
Yes. And so
And
then
then
And so now what?
you can factor that.
it's t plus...
Can we factor it?
I think, yeah, t plus 1, t
Yeah,
minus
t
2.
minus
I
1
think you're
squared.
right.
T minus
Okay,
1
okay. So we have a t minus 1 and a t minus 1. So what's my answer?
T equals 1.
When t equals 1, then velocity is equal to 0. And you can check by plugging in a 1. Plug in a 1, you get, 3 minus 6 plus 3 is indeed 0. So it does indeed work. Alright? And so yes, then the time would be 1 second after 1, when t equals 1 second. That should do it. Everybody get that? So really, any question, it comes down to set the derivative equal to this, or set the derivative equal to that. Set the second derivative equal to this and find this. Or plug this number into the second derivative,
Yeah.
right? Because I could give you the same thing and ask you, what's its acceleration at that time?
Then
What is the acceleration at that time? Let's do this real quick. We had 3t squared minus 6t plus 3. And s double prime is,
6t minus 6.
and we want to know what is its acceleration at time equals 1.
S of 1.
Plug in into the
0.
acceleration, yep, and it turns out to be 6 times 1 minus 6 is a big fat 0. So both the acceleration and the velocity go to 0 at that time. I didn't know that when I wrote that up there.
But
That's
if
just
the
interesting.
velocity is 0, doesn't the acceleration have to be 0? Because how can you...
No.
It could just, it wouldn't change at all.
It would just-
constant.
Oh, shit, it just
Because-
passes through 0, I guess.
Yeah. So the acceleration does not have to be 0 when the velocity is 0. Let's look at it this way. So here its velocity is 0. Yeah.
Mhm.
Although in this case, it would work. I was thinking of a quadratic. I'll think of a good example here. So let's say we had some function and we took its derivative. And its derivative turned out to be, let's do x squared plus 2x minus 1. Yeah? Okay, this might do it. I don't know if it will or not. Now let's take its second derivative. What's its second derivative?
2x plus 2. 2x, yeah.
Plus
Like how?
2. Now, so this is its velocity. Where is its velocity 0?
Yeah, it's x.
X plus 1.
Ooh.
Yeah, this is...
Yeah.
it's
Ooh.
imaginary.
So there we go. We're going to whip out the quadratic formula. Okay. So- No.
Oh, no, it's not.
Shouldn't be. Shouldn't be. So x equals -2 plus or minus 4 minus 4 times a times 1 is plus 4 all over 2a. So x is equal to -1 plus or minus root 8 or root 2 over 2. I went ahead and canceled
Yeah.
that. So -1 plus or minus 2 root 2 should be the zeros of this guy. Take either of those and plug it into that bad boy, and you're not getting 0.
Oh, yeah.
So its acceleration is non-zero, but its velocity is 0. Yeah? And let's think about what that looks like real quick. So we have this thing. What does it look like? Well, -1 and you go 2 and -2. So here's -1 and here's that. This thing is an upward facing parabola like this. Okay. And it has a 0 here at -1. Or I'm sorry, this is so this is f prime. It's just a function, yeah?
Yeah.
And it's here at -1, yes, its derivative will be 0. Its derivative is this guy, 2x plus 2, so he looks like this. Right here at -1, you get a 0. But just because the velocity here is 0, right? This is the velocity. We're drawing velocity. And here's acceleration. So the acceleration is 0, but the velocity is negative. Or I'm sorry, the Wait. Did I do the thing? Did I just do the thing?
What?
Did I just say what you said? It was no. Your question was just because the derivative here is 0.
I was saying, like, if the speed is 0, how would the acceleration not be 0?
Yeah. So here's the speed is 0.
Yeah.
And the acceleration is positive.
Yeah.
Here's the speed, because this is the speed, is 0, but the acceleration is negative. So, as you can see, it is changing. The derivative is in the slope of this thing is in the process of changing right here. Even though it's going through 0, it's still going from steeper to less steep. As we see, that's what's happening here. It's going from steeper to less steep. Happens to be 0 here, right? And that happens to be where the minimum occurs. That's always the case. If you have a 0 here, you will have a minimum. Your slope is 0, right? The slope of this is 0, so it has to be 0 there.
Yeah.
So that way works. That way always works. When your acceleration is 0, you have a minimum or a maximum here. But, okay. Did I waste enough time on that?
I think it makes sense.
Okay, I hope it does. I hope it does.
Yeah.
We're going to get more into this geometry, looking at first and second derivatives to determine geometry of this. But that's going to come a little later. We're not going to do that right now, so I won't be testing you on this. All of this stuff here, this kind of comparison that I've done, that's not what I'm going to be looking for. I'm going to be looking for, can you take something like this and translate that into position, velocity, acceleration. And asking specific questions about velocity or acceleration. Can you give me either a time where that occurs or a value if I give you a time, right? Okay. Okay. All right. So on the homework, was there anything like crazy that you could think of?
I think the hardest part was just getting the things to look like they look
Yeah,
in
that
the
was-
back.
Yeah.
Yeah,
Okay.
that's the hardest. Good.
Yeah, I know. That's hard. That is not nice. Okay, so let's just do a bunch of examples. So, ooh, this one's really ugly. Let's do this. Here's 30. We're taking the derivative. This is all we're doing. Oh, this is number 30 from the review on page. It starts on page 196. And this is number 30. And we are just taking the derivative. Yep, we're just finding y prime. They're giving us y and we're finding y prime. The way they've written it is like this.
So, okay.
They've written it that way. What that means is this. Yeah.
Yeah.
Okay. Yeah, I hate that. Okay. So, what's my outermost stuff?
The square root.
The square root. So in fact, I'm going to rewrite this.
Yeah.
I like to do it. I don't know about you guys.
Yeah.
I prefer doing this.
Yeah.
So, and why don't I go ahead and write this like that?
Yeah.
That's also going to make my life easier. So, taking the derivative of this, what do I do?
It's 1/2 times.
1/2 comes out. So I take the derivative of the outside stuff.
Leave
Leave the inside stuff alone.
to the negative 1/2.
To the negative 1/2. So that's the derivative of the outside stuff. Now
Times
multiply the derivative
just 1/2 x to
of the
negative.
inside stuff. So I don't want to lose my spot here since I'm doing this x to the 1/2 like that. Okay, now derivative of this stuff is what?
Well,
Cosine of
Cosine,
x.
right, the outermost thing is sine, so the derivative goes cosine of
X to the 1/2.
x to the 1/2 has not
Times
changed,
1/2.
times the derivative, yes, and right, if I were doing this, I wouldn't probably take this step, I would just write it out, but just so we're all
Wait,
clear.
yeah.
Alright. I don't want to forget that stuff, I better do something. So what happens here? How do we do this?
1/2.
1 over, or
Oh, yeah.
Yeah, there's a couple ways you could do it, right? And
Just
you
1
could
over
just
2,
say
right?
1/2 x to the minus 1/2, like that. That's a
Yeah.
perfectly good answer.
or
1 over 2 root x.
Or 1 over 2 root x, or 1 over 2x to the 1/2. It all means exactly the same thing.
Yeah.
Right? So I'm going to go ahead and write this. I'll give myself some room here and write this as, what did we have? We have 1/2. This is now in the numerator or denominator, right? We could write it like this, right? Because negative 1/2 means take it in the denominator. Okay. Then it was cosine, and then this stuff, which I could write like that.
Yeah.
So I could write this as cosine x to the 1/2. Don't forget that 1/2 in there. And then all this on the bottom. So that would be 2 root x. Okay? Everybody got it?
Yep.
So we could clean this up maybe a little bit. It would be nice if we could just go
You can't do it.
cosine root x.
Okay.
The 2 and the 2 are 4. Let's
Oh,
go
okay.
root x. And then sine. Oh, and that's all. That's a root, isn't it? Like that. I mean, you could keep it as. You could keep it with 1/2 or whatever, however you want to do it. But ultimately, right? You guys feel good about that kind of one?
Yeah.
Okay. Yeah. Okay. So let's do another ugly one. This is so ugly. Okay. I'm gonna change the letter a little bit because when I draw it, it's a Greek letter, and when I draw it, it's just gonna look terrible. So we're gonna replace it with an A. And it's instead of a lambda, we're gonna do A. So y equals x plus A to the 4th over x to the 4th plus A to the 4th.
There's 2 ways you could do
There are a bunch of ways we can do this.
Quotient.
You want to do quotient?
Maybe.
I like doing
Yeah, we
quotient.
can-
That's fine. So let's do quotient. I know it looks like this,
it. So it's the derivative of x
X
plus,
plus
so
A to the 4.
which is what?
3
4.
x plus a.
4
4, sorry. Times x plus a.
x
to the
plus A raised to the,
Third.
and then we leave that alone.
Yeah.
We leave that whole thing alone.
And
Okay.
then
Now minus
X plus A to the 4th.
x plus A to the 4th.
times 3x to the 4x to the 3rd plus 4x 4a to the 3rd.
Does derivative work?
Is this?
That's a constant.
Oh.
So
It's a
Yeah, yeah.
constant.
First
That's
one.
why I'm doing this one. Because that will mess you up so many times. You just get in the habit. You're like, oh, I take the derivative of this. Yeah, 4x to the 3rd plus 4a to the 3rd. You're not thinking A is a constant. A to the 4th is a constant. So you might as well have something like this up there.
Yeah.
Right? That could easily be
Oh.
A to the 4th. And so if that's A to the 4th, if it's just like this and I told you to take the derivative of that, what would you do?
Just be 4x.
You would just be 4x. And so you got to get in the habit of when you see that, you got to be able to recognize that's a constant. That's why we didn't have to do anything when we took that derivative. We didn't have to do a chain rule. Whereas, if it would have been 2x plus A to the 4th up there, what's the derivative of that? You tell me, what is
4.
the derivative? Okay, so
So it's
4
Times
Times
2x plus A to the 3rd. Times
times the derivative of this stuff, which happens to bring you a 2 out there.
Yeah.
Okay, so where were we? We took derivative of the top, left the bottom alone. Minus off, leave the top alone.
times 4x cubed.
4x cubed is the derivative of the bottom.
and all over
All over.
X to the
X to the
4th plus A to the
4th
4th squared.
square.
Now, on a quiz,
We're done.
you're done. Just leave it there. Okay?
You can factor out a bunch of stuff.
Yeah,
Like-
look, I mean,
Oh,
yeah, you
yeah.
could factor out
The
a
X to the
4.
4th.
The x plus a to the 3rd you could factor out.
You could factor out an x plus a to the, so let's see. X plus a to the 4th. That, I'm sorry, not to the 4th, to the 3rd.
But you can factor out a 4. Oh, because
Out
yeah,
of there,
Oh.
but not out of there. And so now we have x to the 4th plus a to the 4th minus one of those is left, x plus a times
No,
now out of
we can just
4, but now it's just x to the 3rd.
Yeah.
Okay, x to the 4th plus a to the 4th quantity squared. And that looks like it's going to come down some. I mean,
the x to the 4th will go
x to
away.
the 4th plus a to the 4th minus x to the 4th minus
Oh.
a 8.
They all can?
A
8 to the x.
x to
Wait,
the
no.
third.
Yeah. Very good.
Those guys are gone, and now we have a to the fourth minus ax cubed with that other stuff right there, 4x plus a cubed. That's what's left over after we cleared all that out. And then x to the fourth plus a to the fourth squared. Again, is that any better than that? So don't worry about it on a quiz.
Yeah.
That's what I'm going to be checking right there. Don't waste your time. Unless I say there's a bunch of follow-up questions. Like, what would it be? What would the speed be? Or, what would the velocity be at 3 seconds or whatever? Then, yeah. And you might be just fine with that, right? You just plug in a 1 and a 1 and a 1 and a 1. You end up doing the same amount of work if you do all this out. So who cares? Quite frankly. Okay. All right. Yeah. So, however, yeah, even on a quiz, I was gonna say if there's trig stuff, try to simplify. If there's obvious stuff to simplify, please simplify. Like if you have something like this. Maybe that's a theta. Do something like that, just go ahead and cancel that guy out, right? I mean, if it's obvious, just do it. But I'm not gonna like force you to get it into its lowest terms. Is there even such a thing as lowest terms with trig functions? I don't know. Get it all into sines and cosines. Who cares? I don't care. You shouldn't care. So, because that's not the point of what we're doing right now, right? Yeah. Okay. That's an odd one, but I still want to do it. I wanted to do that one. Oh, let's do this. I do want to say, in the, there's something we didn't cover in section 3.4, and you will not be responsible for knowing this. So this was derivatives of trig functions. And at the end of that section, there are a lot of limit questions. Like, for instance, find the limit as x goes to something, 0, of sine 7x over x. There's a method that they use here in this book that you could evaluate that pretty darn easily. I don't care about that because we're going to learn a much better way of dealing with these guys later on. This is, if you remember, you guys should both remember, what is this? Sine x over x. The limit as x goes to 0.
It was 0. Or was it 1? It was 0
No,
or 1.
It was 1.
Yeah.
This one was 1.
Yeah.
And the other one was that. And so basically the way you do these is you take your sine 7u over u and you just do like a substitution. You say, well, let's let x equal 7u.
Okay.
So then u is equal to x over 7.
Yeah.
And so now you just plug those in and you get, and notice that as u goes to 0, 7u also goes to 0. So this is the same thing as the limit as x goes to 0 of sine x over 7.
Yeah.
And then you just bring the 7 up into the numerator.
Oh, so it's 2. Oh.
And so it's 7 comes out.
So it's just,
It's just 7.
And it's just sine x over x, the limit as x goes to 0. And you could say, oh, that just goes to 1, so this just goes to 7. And that's cool, but we'll never do this. Although it's really good to know how to, like, if you have a known limit, and you're trying to find a limit you don't know, doing this substitution thing. But by the end of this class, substitutions you will be good at that, let me tell you. And so this is, I don't think it's necessary to go through that. So what I'm saying is, as you're studying, if you see that, don't think, oh man, I don't remember any of that.
Yeah.
No, don't. Don't waste your time. That's pretty much it. I mean, kind of wanted to do another one of these. Let's just do, I did want to do 35. So here's 35. Y is equal to tangent squared of sine theta. Take the derivative with respect to theta.
The first thing is squared.
Yes, the outermost thing, because remember, this is shorthand. That's shorthand notation for this right here. That was just notation we developed last year to say, hey, it's easier to write this than that, but this is what it means.
Yeah.
And so when you take the derivative, what's the first thing we want to do?
Two.
Take the derivative of the outside stuff, leave the inside stuff alone.
Yeah.
Okay. Now multiply by the derivative of the inside stuff.
Wait, why is there a derivative sign?
I think it's to the 1 here.
That's
Oh.
to the 1.
Oh.
Good catch. That is a 1. There we go. Good catch. Okay. Then sine theta is.
Cosine.
Wait, isn't the inside stuff tan?
Yeah, the inside is tan.
Oh, thank you. Yes. Good. You guys both get points. That's excellent. Tan sine theta. Okay. So what's the outside stuff?
It's just
Secant squared.
Yes, right. So the
Oh.
the derivative of tan stuff is secant squared stuff.
yeah.
Yeah.
Okay, so that's the same as saying secant squared all that stuff, which is sine theta,
Times cos.
times the derivative of sine theta, which is cosine theta. So finally, cosine theta. So putting this all together, we have 2 tan sine raised to the first power, so I'm not going to bother. Then the derivative of this, which is this. So secant squared sine times cosine.
And I don't think anything cancels.
I think a bunch of stuff cancels, but that's fine for a
Oh, yeah.
quiz. Because we have a
Sine.
actually no, because tan of sine would be
Sine over cosine.
sine over cos of sine.
Oh, yeah, so nothing cancels.
And then this turns out to be a 1 over cos squared. So we have cosine squared sine.
Nice.
Cosine's on the top. One cosine cancels.
Oh.
So, but that's
No,
a
no,
cosine
no,
theta, that's a cosine sine.
Oh.
So, yeah. Again, why waste your time on a quiz? This is perfectly good, okay? So you're good to go. Do please be ready for me to give you something like this and tell you to find the tangent line at pi or something, okay?
Okay.
Like, that's a coming. Just like what we did at the very first thing we did today, right? I give you some function and say, find the tangent line at a point. It does not matter what that function is. What you're doing is exactly the same, right? You're going to take the derivative. You're going to plug in a value. You're going to put that into y equals mx plus b, etc., etc. But be able to do it with some crazy looking stuff that's going to have a crazy looking derivative. So, all right, guys. I think that's all I got.